Right, in this section, we're going to learn how to find the area of a polar region, and also then later on find the length of an arc of a polar curve. So if you think back to Calc 1, you know, when we were first learning about finding the area under a curve, and this was, you know, a regular old y equals f of x kind of rectangular coordinates curve. The way that we approached it, you know, we said, oh, look, I can approximate it, right? I'm going to find all these rectangles, right? And we could approximate, we get pretty good approximations. These are, of course, right now I'm drawing inscribed rectangles. And then we just added them all up, right? And then we said, look, I can figure out the exact area, right? If I wanted to make it exact, what I would do is squeeze each rectangle to be like super crazy, you know, skinny rectangle, and then but just use a bunch of them, right? So if I could use infinitely many rectangles, each of which is infinitesimally narrow, then I will get the exact area, right? And we found that area. We were able to add up those infinitely many rectangles, right? That was our introduction to the definite integral. And we just had to draw like one sample rectangle here, right? So the definite integral is our magic adding machine, and when we were finding the area under a curve with rectangular coordinates, it was just rectangles that we used. So in this section, you know, our approach is pretty similar, only we're not using rectangles this time. What we're going to do is cut up our region into a bunch of sectors. So a sector, if you might recall from pre-calculus or tech math, that if you have like a circle, right, of radius r, then if you cut out like a piece of, like, think of it as like a piece of pie, where this could be any old angle at all, so some angle theta, that area is given by the formula A equals 1/2 theta r squared, as long as theta is in radians. So if I take a polar region, and here on the left, this graph is like it's some arbitrary polar region. And obviously, right, it's not a perfect circle, right? So it's not like we're looking at a sector. But what we do is we say we're going to approximate it with all these little sectors here, right? So that's what is shown in the figure on the right. So these are a mix of looks like circumscribed and inscribed sectors. And we know how to find the area of each one of those sectors. Each one of these sectors is a is a theta r squared. So r squared times theta, or actually 1/2 r squared times theta. But in this case, our theta is actually our delta theta, right? We're chopping it up. That's our width. Our little step is that delta theta. And this is how we're going to build the definite integral that's going to give us the area of a polar region. And so if this is how we find the area of a sample sector, then the actual area, I'm going to pull that factor of 1/2 outside. We're integrating r squared d theta, where r squared, of course, is f of theta, right? We with these polar curves, we have r's given as a function of theta. And then our limits, you know, we're respecting theta, so our limits have to be theta limits. And if we look at the figure here, it's just sort of like the lowest value for that, you know, would be this angle right here. The upper value would be right here. So in this figure, we're calling that from alpha to beta. And that's just what we're looking at in the next theorem. This just says how we find the area in polar coordinates, and we're looking at it on an interval, a theta interval, from alpha to beta. Now, the caveat here is that theta interval from alpha to beta has to be not more than a full revolution, right? So that's what this part where we say beta minus alpha is less than or equal to 2 pi. So the full, you know, our range of theta values can't be more than a full revolution. And then we get this integral. Here it looks like two integrals, like we've rewritten it. This just depends on if you rather write r or f of theta, but you know, r is equal to f of theta. We're going to start with an example. We're going to find the area of one petal of the rose curve, r equals 3 cosine 3 theta. It says that it can be shown that the petal on the right is traced as theta increases from negative pi over 6 to pi over 6. So they're encouraging us to find the area of this petal that they've shaded in pink here. They're telling us that the limits of integration are going to be minus pi over 6 to pi over 6. But they do encourage us, right, in this example. Whereas how do we know that? So the petal itself, the bounds of the petal, will be determined. You know, they all cross at the origin here, and that's where r is equal to 0. So we're going to look at the radial lines for r equals 0. Now, if you set r equal to 0 and find theta, right? That's how we find those radial lines for that value, for a given value of r. We get, you know, several values, right? So if I say, okay, I'm going to set r equal to 0, and there's my function r, that means that 3 cosine of 3 theta is equal to 0, and that means that cosine 3 theta is equal to 0. Now cosine is equal to 0 at the top and at the bottom, right, of the circle. That's where the x-coordinate is 0. So that means that 3 theta is some odd multiple of pi over, right? It could be pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, also negative pi over 2, negative 3 pi over 2, right? So odd multiples of 3 pi over 2. Odd multiples of pi over 2, rather. So that means, you know, 3 theta could be minus pi over 2, 3 pi over 2, 5 pi over 2, and so on. Now, these different values will give us the different radial lines, right, that bound each of these petals. And certainly we could find other petals, right, for different values of theta, but if you pick the minus pi over 2 and pi over 2 for 3 pi, that will trace out this petal on the right. And you can verify this, and I always encourage you to verify. We have calculators that we can put into polar form, or polar mode. So I'm going to just put in the function 3 cosine 3 theta. Now I'm going to hit the window. If I'm trying to verify that that petal is sketched out from minus pi over 6 to pi over 6, which is what would be required, right? So if 3 pi is negative pi over 2 to pi over 2, then, if 3 theta is negative pi over 2 to pi over 2, that means that theta would be minus pi over 6, pi over 6. If I'm trying to verify that, then what I'll do is tell my calculator, when I set the window for theta to be from minus pi over 6 to pi over 6. And I'm going to just make my theta step smaller, so that it graphs it a little bit more slowly. We can actually see how it traces out that part of the curve. So I'll set it to like pi over 200, really, really small, and it'll graph it a bit slower. So let's see if I look at this curve, it looks like my x and y can just go from, say, minus 3 to 3 on both axes. Okay, cool. And there we go. We could see that it started here, went down, came up. I'm not seeing the rest of the curve because I told it not to move beyond those values of theta. So this is sort of confirmation that these values of theta, minus pi over 6 to pi over 6, are good limits for this integral. Now, So now let's set up the integral using theorem 39. This area is 1/2 times the integral from minus pi over 6 to pi over 6, and then r squared, so 3 cosine 3 theta squared d theta. I'm just going to square that. Whoops, minus pi over 6, pi over 6. So it'd be 9 cosine squared 3 theta. I'm going to pull the 9 out. So 9/2 integral minus pi over 6 to pi over 6 times cosine squared 3 theta. Now we have to think back. You know, we have all the skills we need to do all the integrals in this section, in this chapter. We just have to think back to all the work we did in chapter 4 with techniques of integration. So this is a trigonometric integral. I have just an even power on cosine, and you might recall from back in chapter 4 that the way we handled these, if we only had even powers, was we used the half angle identity to rewrite it. So this is 9/2 integral minus pi over 6 to pi over 6. Using the half angle identity, we get 1 plus cosine of 6 theta over 2. And now I'm going to just rewrite it one more time before I'm ready to integrate. I'm going to grab this factor of 2, or really it's a factor of 1/2, and throw it outside. So we have 9/4 integral minus pi over 6 to pi over 6. 1 plus cosine 6 theta d theta. And we know how to integrate this, right? We certainly can integrate the constant 1, and the integral of cosine is sine. We just have to compensate for that factor of 6. So this will be 9/4 theta plus 1/6 sine of 6 theta, from minus pi over 6 to pi over 6. Okay, let's throw in our limits. Throwing in pi over 6, we get pi over 6 plus 1/6 times sine of pi minus, when we throw in negative pi over 6, we get negative pi over 6 plus 1/6 sine of minus pi. Sine of pi and sine of minus pi, they're both 0. So this is 9/4 times pi over 6 minus an 8. So that would be 2 pi over 6 or pi over 3. And this would be 3 pi over 4. There's our area. Okay, let's do another one. This one's it's a little bit more going on here. So we have a curve given by the function r equals 1 minus 2 sine theta. It says, and this crosses itself, right? So we can sort of see it cross itself, and we have this small loop, and then it opens up into a bigger loop. It says it can be shown that the inner loop is traced as theta increases from pi over 6 to 5 pi over 6. And the outer loop, let's see, starts at 5 pi over 6 and goes up to 13 pi over 6. And we want the area in between. So, in order to let's see, conceptualize, we basically want to punch out the inner loop from the outer loop, right? If I integrate r squared from 5 pi over 6 to 13 pi over 6, I'll get everything that's shaded plus that bit inside, right? And then what I want to do is punch that out. I want to subtract that. So subtract out the inner loop from that. So subtract out the integral from pi over 6 to 5 pi over 6. And I guess we could just kind of get started. Let's start, I guess, with the inner loop. I'll call that A1. 1/2 integral inner loop is pi over 6 to 5 pi over 6. Now we just have to figure out how do we integrate such a thing. There's not a simple u substitution that's going to work in this form, so I'm going to expand out that product. So we get 1 minus 4 sine theta plus 4 sine squared theta d theta. We know how to integrate 1, we know how to integrate 4 sine theta, and then we have this term that's a sine squared. So in even power sine, we're going to use that half angle identity for sine this time to rewrite this. Using the half angle identity, we get 1 minus cosine 2 theta over 2. Do a little canceling here. Oops. So we have, this factor of 2 here, right, that's going to distribute in. So we have 2 plus 1 for our constant term. So we have 3 minus 4 sine theta minus 2 cosine 2 theta. And now we can integrate all of this. So let's go ahead and do that. Integrating 3 gives us 3 theta. Integrating minus 4 sine theta is a plus 4 cosine theta. Integrating minus 2 cosine 2 theta gives us minus sine 2 theta. And now we just need to plug in our limits. So if we plug in 5 pi over 6, 3 times 5 pi over 6 is 5 pi over 2, plus now 4 times cosine of 5 pi over 6. Cosine of 5 pi over 6 so here's 5 pi over 6. Cosine is negative root 3 over 2. Minus, let's see, 2 times sine of 5 pi over 6, or sorry, 2 times 5 pi over 6 is 5 pi over 3, and sine of 5 pi over 3, 5 pi over 3 is down here, and that sine is minus root 3 over 2. Alright, so that takes care of 5 pi over 6. For pi over 6, 3 times pi over 6 is pi over 2, plus 4 times cosine of pi over 6. You can use the unit circle. that'll be positive root 3 over 2 minus sine of pi over 3 is positive root 3 over 2 and that is 1/2 times, let's see, 5 pi over 2 minus pi over 2 is 4 pi over 2 or 2 pi. Then we've got negative 2 root 3 plus root 3 over 2. Then we have minus 2 root 3 and minus a negative, that'll be a plus root 3 over 2. So let's see what we got. Root 3 over 2 and root 3 over 2 is just root 3. Minus 2 root 3 minus 2 root 3 brings us to a total of minus 3 root 3, all told. Alright, so that is A1, and if we distribute the 1/2, we get pi minus 3 root 3 over 2. That's the inner loop. Okay, so we've done quite a bit of work, but the good news is the outer loop, half the work's already done. We've already done half the work, because for the outer loop, you know, the function we have for r is the same, right? We're integrating the same function. We're just changing the limits. So we don't have to go through and integrate it again. For the outer loop, there's only one t in outer. Outer loop, I'll call that A2. That's 1/2 integral from 5 pi over 6 to 13 pi over 6. 1 minus 2 sine theta squared d theta. It's the same integral, just different limits. So I'm going to take this expression that we already found here, right? And I'm just going to throw different limits on it. And if you go through and plug in all those limits, you'll find that A2 is equal to 2 pi plus 3 root 3 over 2. All right, now we're ready to put it all together. The area between the loops. Is A2 minus A1, right? We had the outer loop, and then we wanted to punch out, you know, or remove that area of the inner loop. Minus A1. So let's see, 2 pi minus pi is pi. 3 root 3 over 2 minus a negative 3 root 3 over 2 is positive 3 root 3. So plus 3 root 3. And that's the area that we're after. Occasionally we may need to find the intersection of two or more polar graphs. And you want to be careful about this. You know, we have algebraic techniques to find an intersection of graphs, right? Generally we say, oh, I'll just set this, I'll solve the system of equations. And that will find some intersection points. With polar graphs, though, you may not find them all just by solving the system of equations. So I want to show you what I mean here. In this example, we're going to find points of intersection of the graph r equals 1 minus 2 cosine theta. So that's one in, like, I guess the darker black, the one that kind of loops around itself. And then the gray one is the circle, r equals 1. We'll note, right, we could see on the graph there are 3 points of intersection. So if we solve the system of equations, right, I have a system of equations, r is 1 minus 2 cosine theta, and r equals 1. So, you know, I could start, we could solve it pretty simply, or at least get a simple approach to this just by using substitution. I know that r is also equal to 1, so I'm going to just plug that in right here. So we get 1 is equal to 1 minus 2 cosine theta, and that means that 2 cosine theta has to be 0. And that means that cosine theta is 0. Cosine theta is 0 at the top and the bottom of the circle. So if we look at one full revolution from 0 to 2 pi, this happens when theta is equal to pi over 2 and 3 pi over 2. And then we get these points of intersection in polar coordinates. In polar coordinates, that would be, let's see, we know r is 1, so it would be 1 pi over 2 and 1 3 pi over 2. Okay, so that's what we get when we solve the system of equations, but clearly we can see we're missing one. The ones that we found are this one and this one, right, at the top and the bottom of the circle. But there is a third point, so let's focus on that. Right? What about that third point? That third point, on the graph of r equals 1, that occurs when theta is pi. So this point is 1 pi. And we could see it's definitely a point on the graph of 1 minus 2 cosine theta, but it occurs at a different angle. So on the graph of r equals 1 minus 2 cosine theta, that point is -1, 0. Now, you might look at that and say, well, yeah, of course it's -1, 0. That's what it looks like. X is -1 and y is 0. But this is the point in polar coordinates. Okay, in polar coordinates, the point is -1, 0. Normally, 0 would be this way, right? That's 0 radians. But since the value of r is negative, that flips it over. So it occurs at a different value of theta. So the takeaway from this example is, if you are working out a problem where you need to see or find out where 2 points intersect, make sure that you throw it in the calculator so you could look at those graphs to make sure that you found them all when you go through and solve it algebraically. And if you're missing one, you could just sort of examine how that might happen. Here it's because we had to use a -r with a value of theta that was off by pi radians. All right, now let's finish up by doing some arc length. We're going to do an arc length problem and then look at a surface of revolution in the next example. So arc length, we did arc length with the parametric equations in the last section, or a couple of sections ago, and this is really similar. In fact, it's pretty much, is a very similar integral, right, that we're working with. It is similar to the one we saw in Chapter 3 when we had a rectangular equation, similar to the parametric equations that we saw in Section 1 of this chapter. So we're just going to do an example, not a formula that you need to memorize or anything. So if we want to find the arc length, and they give us the limits, they say from theta equals 0 to 2 pi for this curve, r is equal to 2 minus 2 cosine theta. So if this is r, I know that I need to find dr d theta. These are the same formula, by the way, right? Those two integrals are the same. The difference is whether you use the f prime of theta or dr d theta notation, but they're equivalent. So I'm a fan of the dr d theta notation. So they give us r equals 2 minus 2 cosine theta. So dr d theta is, let's see, 2 sine theta. And that means that we're going to get the arc length by integrating from 0 to 2 pi the square root of r squared plus dr d theta squared. So r squared would be 2 minus 2 cosine theta squared plus dr d theta squared is 2 sine theta squared. All right, our path forward with this integral, I think, will be just to do some algebra. Let's expand out the product. The 2 minus 2 cosine theta squared. So that'll be 4 minus, let's see, 8 cosine theta plus 4 cosine squared plus, and then if I square that out, I get 4 sine squared theta. Now there's a common factor of 4. So I'm going to take that out. We have a common factor of 4 in all terms in the radical. So I'm going to pull it out of a radical. It'll become a 2, and I'm going to grab that 2 and just yank it right out of the integral itself. When I do that, it'll look like this. So I've taken a factor of 4 out of everything. So we have 1 minus 2 cosine theta plus cosine squared theta plus sine squared theta. Still looking maybe a little messy, but it's going to look a little better once we use the Pythagoras right there. So that's another, just a term of 1. So overall this is 2 minus 2 cosine theta. I'm going to take out the common factor of 2 and then pull out a factor of square root of 2 from the integral. So I got 2 root 2 integral 0 to 2 pi square root 1 minus cosine theta d theta. At this point you can use the half angle identity. 1 minus cosine theta, that is the same as 2 sine squared of theta over 2. And if you want to see that out, right, here's our sine squared theta over 2. For the half angle identity is 1 minus cosine theta over 2. And then we just multiply both sides by 2. All right, we're getting pretty close now. So we have another factor of the square root of 2 we could pull out, right? And that'll multiply by the root 2 that's already there. So we'll end up with 2 times 2, or 4. And then we have this sine squared inside a radical. So we'll simplify that and just have sine of theta over 2. So that gives us 4 times the integral, 0 to pi, sine theta over 2. So, after a whole lot of simplifying, using some identities, doing a bunch of algebra, it's a simple integral to do. The integral of sine is negative cosine. We would need a factor of a half to make that work, right? Because we have 1/2 theta inside, and then compensate with a factor of 2 outside. So this is 8 times, when we integrate this now, is negative cosine of theta over 2. So if I plug in 2 pi, we get minus cosine of 2 pi over 2 is pi, minus a negative cosine, so plus cosine of 0. Cosine of 0 is 1. Cosine of pi is negative 1, so negative cosine of pi is 1. So we get 8 times 2, or 16. We really get to kind of flex a lot of our skills that we gained in Chapter 4 with the techniques of integration. A lot of trig integrals that we encounter in this section. All right, the very last example we're going to look at is going to be to find the area of a surface of revolution. Again, these integrals should look familiar, should look kind of similar. First of all, as compared to the surface area, we see that same radical appearing. We have f squared plus f prime squared inside a radical. Now, because it's surface area, we also have this factor of 2 pi outside, and we have a factor inside, f of theta times sine theta, or f of theta times cosine theta. And this is basically the radius, right, of revolution. If we revolve about the polar axis, that's like the x-axis, the positive x-axis, then the radius should be the y-coordinate, and y is r sine theta, so that's the f of theta sine theta. If we revolve about the line theta equals pi over 2, that's our y-axis, and so the radius would be the x-coordinate, and x is r cosine theta, and that's what we see here. Again, you don't have to memorize these integral formulas, but I just sort of want to explain those factors of f theta times sine theta and f of theta times cosine theta that we see in the different integral formulas. So in our last example, we're going to find the area of a surface formed by revolving the circle r equals cosine theta about the line theta equals pi over 2. So if it's about the line theta equals pi over 2, that means we're using the integral on the bottom. Our radius is r cosine theta. And the first thing we got to observe is that this circle, and we can verify this on the calculator by looking at the graph, but this circle is traced on as theta ranges from 0 to pi. So r is equal to cosine theta. Dr d theta is minus sine theta. So our formula, I'm actually just going to write out the formula first. Alpha to beta, let's see, r cosine theta times the square root of r squared plus dr d theta squared d theta. So this is 2 pi times the integral 0 to pi r cosine theta. Well, r is equal to cosine theta, so r times cosine theta is cosine theta times the square root of, and then inside r squared is cosine squared theta, plus dr d theta is minus sine theta, and then we're going to square that. So we have cosine squared theta times the square root of cosine squared theta plus sine squared theta. And, you know, I think we all see what's coming here. Cosine squared theta plus sine squared theta, that's 1, and the square root of 1 is 1. Right, this whole thing here, that's just a factor of 1. So we're going to just integrate cosine squared theta. We'd have cosine just raised to an even power, like we've seen a couple other times this section. We're going to use the half angle identity to rewrite that. So this is cosine squared theta is 1 plus cosine 2 theta over 2. Going to yank out this factor of a half. So we get pi times the integral from 0 to pi. 1 plus cosine 2 theta. We know how to integrate this. The integral of 1 with respect to theta is theta. The integral of cosine 2 theta with respect to theta is 1/2 sine theta. 1/2 sine 2 theta. And our limits are from 0 to pi. Now we can throw those in there. So when we put in pi, we get pi plus 1/2 sine of 2 pi minus, when we plug in 0, we get 0 plus 1/2 sine of 0. Sine of 0 is 0, so this whole term here zeroes out. Sine of 2 pi is also 0, so just that part zeroes out in the first term, and we get pi squared. There's our surface area. Huzzah! We did it. That finishes up the course. Please reach out with any questions that you have.